Okay, so welcome. It is Friday, January 22, and this is Psych 222. Okay, so today we are going to finish off our discussion of calculus, and then on Monday we are starting in with the first chapter of our book. Now, just a word of warning that it's possible that today's lecture cuts out a little bit, and I have to reconnect just due to a little bit of weather and communication with my tower through which I get the internet. Okay, so what did we talk about last time? Well, we talked about the derivative and we talked about limits and those concepts. So what I've done here is I have cleaned up the screen a little bit. So let's go over those main concepts. Now, remember that last time we said we have 2 points on this curve. So there's the curve right there. And we can draw a line connecting those 2 points. We can compute the slope of that line, and that's not difficult to compute the slope of a line. But what's the key here? The key is we want to see what happens as this point stays the same, but that we bring x2 closer and closer to x1. In other words, we're looking at a change in x, right? We're looking at a change in x. So what happens as we draw more and more points here until we keep getting closer to this particular stationary point, x1? Well, that's what we have over here on the next page. That's what we're looking at over here. So what the author has done here is just move all of those slopes over until they're all just stemming off this particular point. So as x2 goes to x1, what is the slope of the line? Notice that's the change in x goes to 0. That's what that idea is, x2 going to x1. So if I kind of draw this just focusing on that stationary point, I'm going to try to draw the curve about the same. This is what this looks like. We're now at this single point right here. We want to know what's the slope of that line, right? What's the slope right here? Okay. This is the whole idea of what differential calculus is about, is calculating the slope at a particular point. Now we know how to compute the slope of this line, but how do we compute the slope of this particular line? Well, we need to bring in the concept of limits that we talked about the last time. Why do we need the concept of limits here? We need the concept of limits because of this idea here. As x change goes to 0, what's going to happen? Well, look what happens here. As I move this over, x2 is getting closer and closer to x1. Well, how close can it actually get to x1? Well, it can get infinitely close, right? It can get infinitely close. And we need a way to describe that kind of infinite closeness over here. So let me give you an example. Let me put a wall here. And let's say that I'm a person right here, and I am walking towards the wall. Well, as I walk towards the wall, I'm going to at some point halve the distance, right? There's half of the distance. There's another half of the distance. So now I'm over here. Well, as I continue walking, I'm going to halve the distance again. So I've got half here, and I have half here, and then I'm going to halve the distance again. I'm going to keep halving the distance as I get closer and closer to the wall. So think of it that I'm now right next to the wall, right? Here's the wall, and I'm very, very, very close to it, yet there's still a little bit of change in x there, right? There's still a little bit of change in x as I get closer and closer to the wall. We need a concept that's going to describe that eventual getting to that point and incorporating all of those small little changes. The idea of getting closer and closer, right? We are closer and closer to the wall until those little bits of change are extremely small. Well, we saw last time that the idea of a limit helps describe that process, right? So when we say, what's the limit? Well, what's the point we're headed towards, right? What's the point we're headed towards as we get closer and closer and closer? So let's see how we can use the limit concept in describing the derivative, because we need it. We need the limit concept. What we have up here is the idea of a difference quotient, and that's the slope of the line connecting x1, y1 and x2, y2. So this here, change in y over change in x, is called the difference quotient. But so far, when we look at the difference quotient, change in y over change in x, we're still in the realm of what we're going to call just ordinary mathematics, right? There's no real calculus going on here. We're just observing the change in x and the change in y. Where calculus comes in is when we want to consider what happens as the change in x goes to 0. This is really key here. That's fundamental to understanding the nature of a derivative, right? The key is what happens as x2 gets closer and closer and closer to x1. That's why we need the groundbreaking idea of what differential calculus is about. Okay, I just want to reiterate that point. We don't need calculus to calculate the slope of this line. That's high school, right? What we need calculus for is to describe the slope of the line as this change goes to 0. That's what it's about. So how are we going to describe this? Well, first of all, we can describe this part of what we're going to define as the derivative pretty soon. This is going to be called the derivative in a second. But let's just look at this part, because this part, this is still introductory math, where we have the function at x2 minus the function at x1 over x2 minus x1. Now let's look at that idea. Function at x2 minus the function at x1. Well, that's no problem, because the function at x2 is y2. The function at x1 is y1. So f at x2, f at x1, that's what those values are. Remember how you read this, right? Function at x2. Well, that's the value of the function at x2, because that's where it joins up over here. Similarly, the function at x1, there's x1. There's the function value. That's how you read that. Remember how we said last time the idea of f at x. What's the function at the given value of x? So this whole fraction here is easy to understand, because we're just taking f at x2 minus f at x1 divided by x2 minus x1. In other words, what is this really describing here? This is describing the change in y relative to the change in x. Nothing too groundbreaking. Where's the groundbreaking idea? Well, the groundbreaking idea is when we invoke the limit concept, and there it is. What does this statement say? Well, this says as x2 goes towards x1, right? As x2 goes towards x1. And that's exactly what we've been talking about. We said as x2 goes towards x1. Now, how much do we want x2 to go towards x1? Do we want it to go a little bit? Well, if we want to go a little bit, we'd draw it here, and we'd say, well, just go this much, right? We'd say go from here to here. Well, there's our new x2. That's not enough. We want it to keep going towards x1, right? We want it to go all the way to x1 until it's right there, right? That's what all these points are about here, right? All these lines, notice the closer and closer and closer idea, right? That's what we want. So to describe that change on the x-axis, we are not going to settle with the idea of x2 going towards x1. We want the change in x to go all the way to 0, right? No change. That change is actually going to 0, right? So you have x2, x1. There's a bit of change there, but you want x2 to keep going towards x1 until the change is equal to 0. To describe that process of getting closer and closer and closer, that's why we need the limit. So we read this expression to say the limit as the change in x goes towards 0, right? The limit as the change in x goes towards 0, so that eventually in the limit, there's no change. In the limit, x2 is right on top of x1, right? And we go back to our curve. In the limit, x2 is right there, and we are right at that particular point. That's what we mean there. That's how we're using the limit concept. So in the limit, as the change in x goes to 0, well, now what do we have? The function at x1 plus the change in x minus the function at x1 over the change in x. So I drew this up here, change in y relative to change in x. We said that that's kind of ordinary mathematics. That's nothing too sophisticated. This is the sophisticated part because we're now invoking the limit concept and we are describing what we want that change in x to do. We want it to go to 0. And when you add in that limit concept with the difference quotient here, the difference quotient, you get what's called the derivative. Okay, this is the derivative. And what is the derivative? Well, the derivative is simply a slope, right? It's simply a slope. So we know what slopes are, and we looked at a few slopes last time. The derivative is simply a slope, but it's the slope of the tangent line to the curve at that particular point, right? At that particular point. So again, if I go up here, well, let me go to the other one where we have all of them, right? This particular point right here, as I bring x2 closer and closer and closer, eventually I get the slope at that particular point, right? It's right at that point. That is what the derivative is. But to get to that point, to describe that point, we can't simply say there's some change in x. We have to say the change in x goes to 0. And for that, that's where we needed the limit concept. Okay? So the limit concept is describing that closer and closer idea. Now you think, oh, well, that's great. This is like wonderful, right? But what's it for? I mean, why are we even doing this? Well, I'll give you a practical example. If you take, the distance between 2 points, right? You can calculate distance over time and it can give you speed, right? What's the distance over time? And you can find out what your average speed is. That would give you an average speed. So, if I decide to go down the road and I'm going to go to McDonald's, I can look at that distance and I can look at how much time it took me to get there. And then I can calculate my average speed. Now, my average speed from point A to point B, right? My average speed doesn't mean I was going a constant speed the whole time, right? I might have gone faster, I might have passed somebody, then I might have gone slower, gone faster, etc. But on average, I was going a certain speed. What the derivative allows us to compute is the instantaneous speed at a given point. So imagine you are, well, let's do the car. There's the car right there. And you're going from point A to point B. Okay, so you're going from point A to point B. And like we said, well, we can compute the average speed. distance over time to get from point A to point B. But what if we ask this question, right? What if we ask this question at this particular point, right here? So on your journey, you're going along, at this particular instant, right? At this particular instant, how fast are you going, right? How fast are you going right here? How fast? In other words, what is the rate of change at that particular instance? And that is one place where derivatives are used in physical applications. Because if we look at this particular point here on the graph, isn't that nothing more than the rate of change at that particular point? This is the rate of change between these 2 points. We have another rate of change between these 2 points, but right here, right, that slope at that one particular point right here is the rate of change at that particular point. So sometimes you'll hear the derivative talked about in that capacity as the instantaneous rate of change. And that's a pretty big deal historically, that calculus revolutionized the way things are computed. And calculus allows people to compute a lot of things, like orbits around the Earth and launching satellites and all of these things, because it allows to describe that instantaneous rate of change, not simply average rate of change between 2 distant points. Okay. So that's the idea of the derivative. So we say the derivative is the slope of the tangent line at f at x1 right here, okay, right there. And beyond that, well, we can develop computational techniques for computing derivatives. For instance, in this example here that the author discusses, we are going to consider this particular function. That's a x squared, so that's a quadratic function. And what is the derivative going to be? Well, it's the limit of the difference quotient, right? This makes some sense now because remember, the difference quotient is this, and all we're doing is taking the limit as x goes to 0, right? As the change in x, rather, goes to 0. So this goes to 0, what happens? We need the limit concept. That's what this means right here. So how could we compute the derivative of this particular function right here? Well, when you take the idea of the derivative right here and you plug in that function into here, so that's what this is doing. Notice that we're allowing a little bit of change in x. We're also squaring it because we have a square function minus the function x squared, and then we expand all of that. We have our limit concept right here because we're computing something called the derivative. There's the derivative. That's another notation for the derivative. Eventually, we get to 2x. Okay, so we say that 2x is the derivative of that particular function, x squared. Now, you may recognize this if you've taken calculus before. You may recognize this a little bit and you say, you've got an easier way of computing derivatives that you don't actually have to do all of this stuff. Thanks to computational techniques in calculus, we know something called the power rule. And the power rule is one of many rules in calculus that allows kind of like a shorthand so you don't have to plug in the function into the derivative function here. You can just do things like this. You can take this and you can say the derivative is equal to 2x because you're minusing 1 here and bringing the 2 to the front. And that's called the power rule. Now, for our purposes, that's not really important because we're not going to be doing a whole bunch of calculus and having to memorize these rules. But if you've taken calculus before and you remember that, that's all you're doing is you're using a convenient rule to compute the derivative. And we know there's other rules too. There's the chain rule. And that's what you're doing when you're using those rules, is you're just doing a computational technique to get the derivative. But ultimately, you're getting a derivative. Okay, so that's what that's about. Okay. Rules for manipulating derivatives. Those are, there's a whole bunch of rules. We're not going to go through all that. If we were doing a complete calculus course, we would, but we aren't. I just want to point something out here, is that derivatives are often used for determining where the slope is equal to 0 on a curve. So here we have a particular curve. It's going like this. Well, we know that the derivative is a slope. So if the derivative is equal to 0 here, then we know that that's a particular maximum of the curve. Same thing here. We know that this is a minimum of the curve. Why is that? Well, if I just draw a simpler curve here, watch this one, like this, and I want to know where's the highest point in the curve. Well, if I compute the derivative right here, well, that's still at a slope, right? But if I want to know where that highest point is, it's going to be the point at which the derivative is equal to 0. Because notice that this particular line is touching that point and the slope is equal to 0. So that's often an applied technique of where the derivative is used is for finding maximums and minimums of functions. And that's used all over the place, in engineering, in statistics, in computer science. They're always finding maximums and minimums of functions. So it's a really, really common use of the derivative. And it's kind of convenient because then you know where the top of the curve is and where the bottom is. Many algorithms in machine learning and things like that often try to find minimums of functions. So oftentimes what your computer is doing is when you're performing these algorithms is seeking a minimum value. And oftentimes it's using techniques of calculus to find that. Okay, so that's it for our discussion of differentiation. And there's a lot more. There's even multivariable calculus there and some other applications. The second big idea to calculus is the idea, I think I'm almost there. One more. The idea of integral calculus. So far what we've talked about is differential calculus, and differential calculus is about finding derivatives. Okay, so that's what we've talked about with the derivative so far. But there's another side to calculus, which is integral calculus. And again, if you've taken a calculus course, this looks familiar. And we're going to see how this is used. So we're going to define the idea of a definite integral in a second. Integral calculus, its job is to find areas under curves. Now let's motivate this with a really easy example. We know how to compute the area of a rectangle, right? Length times width, okay? So if I put length and I put width here, I know how to compute this area. We also know how to compute areas of other things too, triangles, circles, and a whole bunch of other things. So historically, computing these areas was relatively easy. And again, that's kind of that elementary mathematics before you get to the ideas of calculus. What calculus is able to do is it does something like this. Instead of taking shapes like this, what if we wanted to compute the area of this particular shape? Well, how would you compute the area in here? Easy up here. This was easy, right? For this like rectangle and squares and stuff like that, it's easy. But how about for this? Well, it becomes much harder. So how might you approach the problem? Well, you might approach it by doing this, doing what you know, right? Maybe computing one rectangle here. That's not going to be perfect there. You're going to have a little bit of space here, right? Notice that little bit of space that I wasn't able to include? because I have to make it into a rectangle. What if you computed the area of this rectangle, and then you computed the area of a rectangle next to it, and then another rectangle, another rectangle? What happens is when you compute the areas of those rectangles, it's not going to be perfect, right? So I'm going to just kind of blow this up over here, magnify it, right? When you try computing those rectangles, you're allowing for a little bit of space. Sometimes it's over, sometimes it's under, something like that, right? It's not going to be perfect because you're going to have those little bits of information in there. But nonetheless, it's a pretty good approximation. Approx, A-P-P-R-O-X. It's a pretty good approximation to the true area in that shape. So if you computed all these rectangles and then you added them up, right? You summed all of the rectangles, that's the summation sign. You summed up all of those rectangles, you would get a pretty good approximation to the area in that shape. And that makes sense as to why that should be, right? Well, look what calculus does. Calculus looks at all of those little rectangles, right? All those little rectangles under the curve, they're usually not slanted. That's just showing the area under the curve. There they are. There's all my little rectangles. See how there's a little bit of space there, a little bit of space there. So the approximation isn't perfect, right? The approximation isn't perfect, but still we're showing that we can take a value, we can add a little bit of change, produce the rectangle, and have a whole bunch of rectangles. If you want to know the actual area under that curve, the solution is to sum them up, right? You are going to sum all of those rectangles. Well, you're going to sum them up, but the approximation still isn't going to be perfect. So that's why this says approximating the area under the curve by summing the areas of rectangles. It's still an approximation. Why is it still an approximation? It's an approximation because we're still using a rather crude technique. We're trying to compute rectangles under a curve, just like in our shape earlier. We're trying to compute all these rectangles under a fancy curve. So it's still going to be approximation, but we'd like to get the true area. So how can you get the true area? Right? How can you get the true area? Well, to get the true area, you are going to have to invoke the limit concept. See how limits are seen again now that we're computing integration? So we said that computing all of those rectangles is an approximation, but the approximation, right, the approximation is going to grow better and better as the number of rectangles increases and the change in x grows smaller, right? What's the change in x? Well, the change in x, if I can go back, is this right here. So I have x sub naught plus a little bit of change. Well, imagine if I made that change smaller and smaller and smaller, and then I added up all of those little rectangles. What would I get? I get an extremely good approximation as the number of rectangles increases and the change in x grows smaller and smaller. Well, how can we describe this growing smaller and smaller and the number of rectangles increasing? How can we describe this idea? We describe this idea by the limit concept, where I'm going to highlight this over here. Notice that the change in x goes to 0, right? The change in x goes to 0, and look at this. N goes to infinity, right? N goes to infinity. An infinite number of those small rectangles. Wow. Using the limit here really helps. Notice how you need the limit concept. Otherwise, all you're doing is getting that approximation. It's the limit concept that allows us to take the approximation and get us to the true area under the curve. So the function at x sub 0 plus all of those little changes. That's what that's doing. So this is the function along the y-axis times the change in x over here. Starting at I equals 0 up to n minus 1, and you are adding up all of those little changes. And that's what this concept of the definite integral of the function is about. Going from x sub 0 to x sub 1, the function dx. And you can think of dx as those like little changes in along the x-axis. But that's how the area is computed. Now, what does this fancy symbol mean? Right? Well, that's the integral symbol. And what that really means is sum. That's all it is, right? You're summing all of those little values. And again, you need the limit concept, because if you don't have the limit concept, you can't get infinitely close, right? You got to get smaller and smaller and smaller. You got to be able, the limit concept allows us to describe this process, which is crucial to it. So we say x sub naught 0 and 1 give the limits of integration, while the differential dx, which we just said, is the infinitesimal remnant of the width of the rectangles, right? It's the smaller and smaller and smaller. So remember I said it's kind of like that little change in x. The symbol for the integral is an elongated s. So imagine we're writing s and we just said, just write it this way. That's what that idea is. It's the continuous analog of a sum. Okay. So why would we want to compute this? I mean, you know, again, we motivated the derivative a little bit, but why would you want to compute something, the integration under the curve and computing areas under the curve? Well, later in the book, when we get to this normal curve, right, we're going to get to a normal curve, and that normal curve is going to have what we're going to call z values over here. And we're going to talk about areas under the curve. Notice that if I talk about the area under the curve between 2 and 3, that's that space right there. That area had to be computed, not by traditional means, but by using advanced calculus to get that particular area under the curve. So these ideas of computing areas under the curve is going to return when we look at some distributions in statistics. Now, we're not going to be computing those using calculus. There's no point in doing that. But when we say in our course coming up, when I say that like the area here is equal to a certain amount under the curve, I'm going to say, you remember when we talked about integral calculus? Just so we have an idea of where that area is actually coming from. Okay? And that's what integration here is about. Okay. Again, here's the, you know, it's describing the process of getting all those little rectangles under the curve. And this particular curve is pretty arbitrary, but you know, you can try a different curve and compute all those areas under the curve, etc. And again, that's important because we're going to see those concepts later in the course. Okay, so that's it for our calculus review. And just to kind of summarize here, okay, what have we talked about? Well, we've talked about differential calculus, differential calc, and differential calculus is looking at instantaneous rates of change. So, you know, change in y, change in x. And what's the calculus part? Well, the calculus part brings in the limit. The limit as the change in x goes to 0, right? That's that big idea here. Notice that we needed the limit concept. This was not enough to describe instantaneous rate of change. That's the big idea. Differential calculus computes derivatives. And what's the derivative? The derivative is the slope at a particular point. Okay, that's the big idea. So, if you did take calculus before and you're computing derivatives, you're computing rates of change, you're computing slopes, but at particular points to describe this idea here. The second big idea that we've just talked about is integral calculus. And the idea of integration is what we're just looking at here. It's computing areas under curves. And it does so by approximating a whole bunch of rectangles that are made really, really small and summing up all those things using a to b of the function. Okay. Now, when you look at these two concepts, you see that there's a general theme here. And one theme that comes about is the idea of approximating and then taking that approximation to the limit. Okay, what do we mean by that? Well, in the case of calculus, I'm going to draw my slope here. We're bringing this point closer and closer and closer and closer to right here until we get to that slope. Notice that we start off with an approximation, and then we refine the approximation by going to the limit. Change in y relative to change in x, but refine it now by taking it to the limit. So you see that this concept of limit is extremely important, both to calculus here, differential calculus, and to integral calculus. Because integral calculus, we did the same type of thing of approximating. We took rectangles and then we made them smaller and we added them up. Until we said, well, how much are you going to do that? How many rectangles are you going to take and how small are those rectangles going to be? Well, I don't know. How do we describe that process? We describe it through the limit again, right? The limit. So those change in x values becomes really, really small, and it's the limit of those values, the limit, that allows us to describe that area. That's the idea here, is in both cases, the limits are used, the concept of a limit is used to describe the kind of eventual number that we're going to get, right? The eventual number as the approximation gets better and better. And that's one of the big ideas we want to take away from this discussion of calculus. Okay, so that's it for today. Again, we are now done with this appendix. So if you've enjoyed this appendix, great. If you haven't, we are into the book on Monday. We started on chapter 1. But these ideas will return now and then, and we'll make mention of them a little bit as we go out throughout the book. Okay, so that's it for today, and we will see you Monday as we start into our stats book.